Okay, welcome to the third example in the chapter of strain. The question reads, the block is deformed into the position shown by the dashed lines. Determine the shear strain at corner C and at corner D. Okay, so in terms of givens in this question, we are not given much, so we'll just write diagram. But there are two important formulas that we must define in terms of like shear strain and what it represents in a formula, and then what it represents physically. Because this formula specifically, you have to know what it means, like physically on the diagram, or you can really mess up. So we'll start with the equations though. So shear strain is equal to pi over 2, which is basically 90 degrees, but we'll get to why you never call it 90 degrees. So pi over 2 minus an angle theta, okay? For the most part, okay? It's not always true, and we'll see this in this question. Shear strain is also equal to the inverse tangent function of x over y. What is x over y? What is theta? Well, to understand this, we have to look at the diagram and see what shear strain represents, because now you can see we've basically completed the collection, right? We started with normal stress, and then shear stress, and then normal strain, and now shear strain. So what does shear strain represent, right? If you look on this diagram, shear strain is an angle in radian. Oh my god. Shear strain is an angle in radians that represents this kind of deformation. So it's like a deformation angle, kind of, right? So it's basically this angle right here, or in this case, it's this angle right here. So that is shear strain. That's what we mean by shear strain. What is theta and what is x over y? Well, if we look at corner D, and if this right here is 90 degrees, or pi over 2, or pi over 2, let's not call it 90 degrees. If it's pi over 2, and this angle right here is theta, I can easily find gamma by simply pi over 2, or 90 degrees, but please don't say that, minus theta, yeah? Okay. What's x over y? Well, it's basically the same thing. If I know this distance over here, x, and I know this distance over here, y, I can find gamma, the angle, using the inverse tangent function, because tangent, in this case of gamma, is equal to x over y, right? So that's what it represents physically, right? Why did I say that this formula isn't always true? Or you can even alter this one by using sine and stuff, but like, why is this one not always true? Well, if we look at this case right here at angle C, sure, this is 90, and this is theta, and let's say this angle right here is phi, or this full angle right here is phi, right? In this case, gamma is not equal to pi over 2 minus phi, right? Instead, gamma is equal to phi minus pi over 2, right? If, again, phi represents this full angle right here, and this is 90 degrees, you want to find theta, it's literally just trigonometry. So these are just general forms of these equations. But you have to understand it for two reasons: to understand what basically we just did, and also to understand the sign convention, which I think we'll explain later in the question, not now. But okay, that's the overall concept of what shear strain represents. Okay. We can start by saying unknowns, or we can move on to saying unknowns and what we want to find. And then we'll quickly draw out the diagram, just clear our stuff. So we want to find the shear stress, or the shear strain at corner C. I think the question does this. And we want to find the shear strain at corner D. One very, very, very important thing we forgot in givens is these two equations only work in radians. Like, I cannot I cannot stress this enough. I cannot strain it enough. Yeah. Oh, okay. It has to be in radians, or like you deserve to get it wrong. These equations have to be in radians when you're doing it, like when you're plugging it into your calculator. Yeah. Okay. Let's move into the diagram. Because like the concept again is very simple, like it's literally just trigonometry, but there are like a lot of ways to mess up. So yeah, if we draw a quick y and x axis, so this is y, this is x, It's going to be very rough because I don't want to make this video too long. Kind of like so. Right? How does this look like? This is A prime. This is B prime around here. This distance over here is 100 millimeters. This is also 100. This is 110. This, I believe, is 15. And this is 85. I hope I'm done now. Yeah, I think I'm done. Let's add in the angles that are going to help us define this formula. Because in this question, I think it's easier to use this one. But inherently, we're basically also using this. Okay, so what do we want to find in this lovely diagram? Well, we want to find, I know it's not to scale, but we want to find this shear strain right here at corner C. I want to find this shear strain at corner D, right? To do that, I'm going to find this angle right here, and we'll call it phi, or actually we'll call this one theta. And I want to find this angle right here, phi. Okay? To find phi, I can, and if this is straight, right? Let's find theta first, okay? Theta is basically equal, if sine of theta, if you look at the diagram, is equal to, yeah, okay, sorry, I just got messed up a bit. Okay, the angle theta is equal to pi over 2 plus this gamma angle, right? We can easily find the gamma angle. I know that that's what we're looking for. Bear with me. We'll get to why I'm doing this in just a second. We want to find this gamma angle. So theta is basically equal to pi over 2 plus this gamma angle, right? Okay. Well, this gamma angle can easily be found using the sine function. It's just the inverse sine of 110 or 15 over 110, right? Using this triangle right here, I can easily find it, right? So it's opposite over hypotenuse. So that's what I'm going to write. It's the sine inverse of opposite over hypotenuse. So 15 millimeters over 110 millimeters. And that'll give me this angle theta. How about phi? Phi is very, very similar in that this time, all I'm going to do is subtract. So it's just 90 or pi over 2 minus this gamma angle right here. Right? And this gamma angle can be found similarly. It's the exact same. This distance right here is 15. This is 110. Right? So it's just sine inverse of 15 over 110. Again, opposite over hypotenuse. Right? When I do these calculations, it will give me the angle phi and the angle theta, again, in radians. It has to be radians, okay? So let's write this down in proper form. So to find the angle theta, and this is our fourth step, so we're going to say find angles. And we'll get to why we're doing this the long way in just a second. Sorry, bear with me. So again, we said theta is equal to pi over 2 plus the inverse sine of opposite over hypotenuse, 15 millimeters, over 110 millimeters. We said phi is equal to pi over 2 minus, okay, sine inverse 15 millimeters over 110 millimeters. Okay? This will give you two angles in radians. It'll give you 1.70758 radians, which basically, if you convert, is about 97 degrees. And then you will also get 1.434006 radians, which is basically about 82 degrees, okay? Why did we do this longer way? Well, number one, it's much easier to use, like, basically, we want to use this formula. I know you could have taken a shortcut, because this is basically your gamma value. This is what the question is looking for, right? You could have just easily skipped to this, to be honest. But we want to do it the long way and try and use these formulas, okay? So that's why we did it. And we also did it because if you do this calculation right here, and if you do this calculation right here, you're going to get two positive values, okay? And we'll see that in just a second. The issue is, the tricky thing with shear strain is the sign convention, okay? You don't know if it's positive or negative. There's a very specific way to see if it's positive or negative, and that stems from this formula over here, which we will explain in just a second. This question is very, very easy, but there's so many things that like can go wrong, like small, minute details, but we'll get to it in just a second. Bear with me, yeah? Okay, so we found the angle theta and we found the angle phi. Using these two angles, we can find shear strain, even though we already found it, but we can find shear strain using this formula, formally, right? Okay, let's do that. So, number 5, we're going to find shear strain. Beautiful stuff. Okay, so from the beautiful formula above, we know that shear strain, or even just trigonometry, you guys, easy by now, you know that at corner C, it's simply equal to theta plus pi over 2, right? It's theta, this, or minus pi over 2, my bad. So it's theta minus this angle here will give you the resultant shear strain, right? Basically, we're doing the inverse of what we did up here. So let me replace that. So it's theta. I'll write down the full value, 1.707586 radians minus pi over 2. Remember, it has to be in radians. You're going to get your shear strain value. Same thing with corner D, but this time we're going to do pi over 2 minus the angle phi. Pi over 2 minus the angle phi, right? So it's just 90 minus this angle will give you the shear strain angle. So 1.434065 radians, right? What will you get? You'll get a value of 0. Or a magnitude for that matter, 0.136789 radians for both of them. Okay, is that your, and that translates to about 7.8 degrees. So shear strain about 7.8 degrees, but it should be in radians. If you keep your answer like this, it's wrong. Why? Because the formula doesn't do this for us. Shear strain, and it won't do it for us. We have to realize it. Shear strain is negative for both of these angles. Why do you say that? One is decreasing into the body, one is coming out of the body. Like, it would, like, if you're looking at it logically, like, it kind of makes sense. Maybe if this one was, for example, negative and this one was positive, okay. But why are they both negative? Well, that stems, and we'll fix right now, we'll say that from diagram, we know that they're both negative, and I'll explain it, and you guys can leave after this, yeah? So, they're actually both negative from diagram. Okay, so we can add a negative right there and a negative right there. So we have negative strain, a negative shear strain value of 0.136789 radians at corners D and at corner C. Why? Well, it stems again from this tangent formula right here, right? Tangent of gamma is equal to x over y. If we think back, and an easy way to do this, like, I don't want to give you like the theory of why this works, but if you remember to the unit circle, right? The unit circle, where you have all your angles, if you think of the tangent function is positive if you think of the cast rule, right? Cast is right here. The cast rule. Sine and cosine are positive in their respective quadrants, right? However, tangent, and they're also positive in the all quadrant, right? Tangent is positive in just these two quadrants, right? Quadrant 1 and quadrant 3. Is that correct? Hopefully it is, or I said it, so it is, right? Therefore, it's negative in the sine quadrant and in the cosine quadrant, okay? When we're looking whether a shear strain is positive or negative, we have to see what quadrant it lies on, or it drops into. And how we do this, remember, where this stems, I don't want to, like, this is just the theory behind it, where it stems is from this unit circle idea, right? Because tangent is, the function tangent is positive in quadrants 1 and 3. So A, all, and T. And it's negative in the sine quadrant, quadrant 2, and in the cosine quadrant, quadrant 4. Okay? How does this translate to here? Well, I'm going to draw a little thing on my little like diagram, I guess. That's one of the reasons I redrew the diagram. And I'm going to see where, again, this angle, this shear strain angle falls into or drops into, right? Well, here I can easily see that it drops into the sine quadrant, right? And if we're looking at the tangent function, this is positive, negative, right? It drops into the sine quadrant, and therefore it is negative, okay? Similarly over here, amazing. Similarly over here, remember I have positive, negative, it drops into the sine quadrant, the negative quadrant, and that's why my answer is negative, okay? And that's practically how you do it. You don't even need to know the CAS stuff. But like basically, whenever you want to see if a strain angle or a shear strain is positive or negative, you draw a little coordinate system on your point that you want to see. And then you see, for example, let's also say that this, I don't know, let's say it was like this, for example, instead. This would be my shear strain angle, right? I draw a little coordinate system, and therefore this would be an example of a positive strain, right? Because, again, it goes into the all quadrant. But, yeah, hopefully that was understood. The math is very simple. It's basically trigonometry, right? It is trigonometry. The only issue, and it's very easy, but the only issue is sometimes this diagram stuff, the sign conventions can get a bit confusing, but at the end of the day, an easy way to do it is you literally just draw the coordinate system on the point where you want to find the shear strain, and you see what quadrant your shear strain angle drops into, right? I'm repeating this for sake of being clear, right? It drops into, in this case, the sine quadrant, or you can just think of it as positive, negative, and therefore it's negative. If it would have dropped into the all quadrant or the positive quadrant, quadrant 1, it would be positive, and similarly, you hopefully get the point, yeah? Wonderful stuff. That is your final answer for this question.